In preparation for next week's lesson, let's go ahead and talk about how to take derivatives of production functions. Recall the production function measures total production in a factory, we'll call that capital P, given investments in labor, capital L, and capital, capital K. When we take the derivative, the partial derivative with respect to capital, to K, we call this the marginal productivity of capital function. So this is a measurement of how production is changing as your capital investments are allowed to change. So the title perfectly sums up what it's doing. Marginal productivity of labor is looking at how the productivity is affected as labor investments are increased or changed. So suppose we have a production function that looks like this. P of Lk is equal to 1.01 L to the 0.75 times K to the 0.25. In this example, notice that the two powers add up to the number 1. It turns out that this is by design in many of the Cobb-Douglas production functions, and the fact that they add up to 1 is going to come in handy for us in the next topic. This is just one example of a Cobb-Douglas production function. We're going to go ahead and do some marginal productivity of labor and marginal productivity of capital computations here in preparation for the next topic. So let's start by taking the marginal productivity of labor. We'll start by rewriting the production function with all of the constant multipliers separated from the variable piece. In this case, we're taking the marginal productivity of labor, or the partial derivative with respect to L. So L is the variable, and therefore K to the 0.25 and 1.01 are the constant multipliers. So once we have it rewritten, we can then take the partial derivative. The way we do that is we take the 0.75, we bring it out front, we multiply by the existing constant that's there, 1.01, K to the 0.25. Then we keep the variable L, but we reduce its power by exactly 1. 0.75 minus 1 is negative 0.25. Now let's clean that up. We're going to use not only basic arithmetic, basic algebra, but we're also going to use rules of exponents to do that. The 0.75 times 1.01 becomes 0.7575. K to the 0.25 just stays where it's at. But notice L to the negative 0.25 goes down into the denominator and the power changes to a positive 0.25. This is a basic rule of exponent that says x to the negative power can be rewritten as 1 over x to the positive power. Doing so will be useful for us in the next topic. We want all of those powers to be positive. In WAMAP, here's how you would enter this to avoid any kinds of results that are inaccurate. I'd encourage you to use that preview button to make sure that what you type is being interpreted correctly by WAMAP. To find the marginal productivity of capital, we basically repeat that process, but now we think of K as the variable and we treat L as a constant. The first step is, as before, to rewrite the original production function so that the variable piece, K to the 0.25, is on the outside of the parentheses, and the constant portion, 1.01 L to the 0.75, is inside the parentheses. Keep in mind, again, we're taking the partial with respect to K, so L behaves like a constant here. So we can go ahead and take partial derivatives at this point. So we can go ahead and take the partial derivative of K at this point. The way we do that is we take the 0.25, we bring it out front, we multiply that by the constant, keep the variable K, and reduce its power by 1. So that's what's happening here. We're using the basic power rule. So what we're doing here is just using the power rule. When we go to clean this up, we end up with 0.2525 L to the 0.75 over K to the 0.75. So 0.25 times 1.01 gives me 0.2525. L to the 0.75 just stays where it's at. And because K has a negative power, we'll take it down to the denominator and convert its power to positive. So this is the partial derivative with respect to K, and this is how you would enter that into WAMAP. So now let's go ahead, now that we have the marginal productivity of labor and marginal productivity of capital functions, let's go ahead and evaluate those at particular values for labor and capital. Remember that the partial derivative with respect to L was given by this expression here in the upper corner of the screen. So we're going to evaluate that when the investment into labor is 16 units and investment into capital is 81 units. Here again, remember, the units can be anything that makes sense. They can be $16 and $81. They could be $16 million and $81 million. So the units aren't too important right now. What's more important is how to interpret what the derivatives and what the numbers mean. So when I take 16 for L and 81 for K and plug it into the marginal productivity function, I end up with this series of calculations that you can see here on the screen. I'm not going to do them individually here. I'm just going to give you the result and encourage you to make sure that you can reproduce that on your calculator or with whatever tool that you're using to do these kinds of calculations. So the marginal productivity of labor is about 1.13625. I've included several decimal places. Again, in case you're thinking about measuring this in terms of millions, then the decimal places will have some meaning. So when L is 16 and when K is 81, when 16 units have been invested into labor and 81 units invested into capital, then production is changing at the rate of 1.136 items per additional unit of labor invested. So the idea here is that we are slightly increasing the amount invested into labor. We're keeping the amount invested into capital fixed, and we're measuring how much change that produces in the overall production levels. So a 1 unit increase in labor investment produces a 1.13625 unit increase in overall production. We can do a similar calculation for the marginal productivity of capital function, plugging 16 and 81 into that function. And when we do that, we get 0.07481. So when labor investments are 16 units and capital investments are 81 units, the rate of change of production with respect to capital K is 0.07481 units of production per unit of capital. In other words, if the labor units are fixed at 16 and we invest one additional unit of capital into the system, so go from 81 to 82, then my production will rise by about 0.07481 units, however production is measured. So all other things being equal, if you're at this combination of labor and capital, L equals 16 and K equals 81, and you have only 1 unit to invest in either labor or capital, assuming that they both cost the same, then you'd want to invest it into labor because that would give you more production for that additional investment into labor. So this example gives you some idea of how we can use derivatives to make decisions, to figure out what's going on. When you have multiple variables at play and you want to try to figure out what each one is contributing to some overall quantity that you're trying to measure, partial derivatives give you the ability to keep all the other variables except the one that you care about fixed, and then say, well, let me change this one variable and see what effect that has on the overall quantity that I'm trying to measure. Very powerful, very useful. And in the next topic, we'll talk about how to use these multivariable derivatives to optimize our quantities. So this concludes this topic. You're ready to start the lecture project and then move on to the homework and the quiz.